Welcome to the Montgomery County Public Schools Algebra 2B Semester Exam Review. This video will cover Unit 4, pages 14 to 17 in the final exam review packet. So, let's read this problem. So, problem 22. As a science assignment, Kylie and Kristen are asked to write a report on how the distance from a light source affects how a person's eyes view its intensity. They purchase a light intensity meter and a flashlight. They move the meter away from the light and measure the intensity at different distances. Here is some of their data. So at 1 meter away, the light intensity had many lux, 320 lux. After 2 meters, it was down to 80. After 3, so it's definitely decreasing. Okay, so Kylie would like to present this model in the form of a table as their complete report. Is this a good idea? Explain why or why not. Well, we're given some data, but we don't really know exactly what the relationship is between the distance and the lux. So I would say probably not. This would probably would not be a great final report. There's no explanation about what they did. It's just data. So there was no explanation about what was done. And you only have 5 values. So what about the in-between values? Or what if I wanted to know 10 meters away? I couldn't really find that on this table. So the relationship isn't quite clear. We're given a limited amount of data. All right, so Christine does some research and finds that the intensity of light, we're going to call that I for intensity, varies inversely as the square of the distance d from the light source. After doing some calculations, she presents this model as a formula, I equals 320 over d squared. We need to show that Christine's formula gives the same results as Kylie's table for t equals 2 and t equals 4. So this is t equals 2 and t equals 4. But I feel like maybe it should have said d equals 2 and d equals 4. So I think that may have been a typo. So I'm going to change that to d. So we know when the distance was 2, the lux was 80. And when the distance is 4, the lux is 20. So we want to make sure that if we plug those data points in, we'll get the exact same values as the table. Okay, so let's go ahead and plug it in. So I'm going to say I, with the distance of 2, I of 2, kind of like our f of x notation, right? So function notation, the intensity with a distance of 2 is going to be equal to 320 divided by 2 squared, right? So I'm plugging in that value of d. All right, so 320 divided by 4, and I get 80. All right, does that check out? When d is 2, intensity is 80. Yep, looks good. All right, and then we also want to check intensity is 4. So go ahead and try that real quick. Check it. I'll pause for a second, and the answer will pop up. Make sure you try. All right, so you should have gotten 20. Great. You know, I didn't mention in the beginning of this video, it is best if you've already tried these problems. Then when I go through them, you can be checking your answers. All right, good. So what are the allowable values for d in Christine's formula? Well, she started at 1 meter away. So if I think about, okay, here is the light meter, right? And if I go positive 1, 2, 3, 4, 5, okay, I can go that way. I could be so close, it was right on it, right? I can't really be 0. But if I'm behind it, it's not going to sense it. I feel like the sensor is just on one side. So I guess that would be something we need to know about the sensor. Is it something you can sense from all sides? Could you go backwards and forwards? But if it was a light sensor that sensed just in one direction, we would say it's greater than 0. Anything on this side, we can, yeah, any values of distance greater than 0 would make sense. Another idea is to say all positive real numbers. The other thing we want to consider is even if we were back here behind, distance, we always talk about distance as being positive. Okay. So then Kylie thinks that a graph would be a good model, so here's her graph. One thing that I noticed about the graph is I don't see labels, so it's really important that when you see a graph, you identify, okay, wait, is this the distance or is that the distance? So we want to find a point, 1, 320. If I go to 1 here, and I go up to 320, yep, I see it right there, except it's so small here you can't really see it. But on your paper you could find 1, 320. So it looks like this is our distance in meters. So I think it's a good idea to write that down. And this is our intensity in lux. Sorry, forgot to write meters. All right, so Jake wants to know what distance would result in a light intensity of 1.6 lux. Which model, the table, the formula, or the graph, do you think would be the best model to use in order to answer Jake? In your answer, tell how you would use the model you chose and why you didn't choose the other 2 models. So let's go ahead and list out the 3 different models. One option is the table. One option is the formula. And the last option was the graph. Okay. So maybe let's start with the graph since it's the last one we talked about. If I were to try to find 1.6 lux, oh my goodness. Well, it's so blurry here I can't even see, but the first little dash is 10. So I need to find 1.6. It's somewhere down here, maybe over there somewhere. I can't even tell. Okay, so the graph would be very hard to see. Very difficult to see, especially with the scale that they have. So we would go 1.6 up on the y-axis and go over till we found the x, but it's really hard to see, so I would not use this one. All right, formula. Well, let's jump back to the table. Okay, so table, distance, lux. I want to find 1.6 lux. Well, it's not really on the table. Okay, maybe I could try to find a pattern to keep going, but to find 1.6 lux, it's going to take a bit of work. So I'm not a huge fan of the table. So if I use the table, I'd need to continue the lux until I found 1.6. When I say continue the lux, that doesn't make any sense. Really what I mean is I would need to measure this again. I'd have to go and play with the light meter until I found a lux of 1.6 and then measure how far away I was. So I would need to collect more data is what really we need to do there. So this isn't ideal. I mean, we could do that, but maybe the lux meter already got returned. I don't know. Okay, so I would not use this either. I could, but I think the most efficient and best option would be to use the formula. So if we use the formula, The formula provides us um, any value. So if I plugged in, so I have intensity equals 320 over d squared. I want my intensity to be 1.6. 320 over d squared. I could multiply both sides, divide and then square root, and I could find that the distance is about 14.14 if you do the math, but I would definitely use formula because I could find any value. Okay? All right. Wonderful. All right. Problem 23. So this graph, I'm going to try and do my best to kind of draw it. It's not exact, but it's hard to see, so I'm going to make it a little easier to see. It's something like that. So the question is, name the two different function types that are added to produce each graph below. So we have two different shapes combined here, right? If I think about the midline of my sine curve, right? I either have a sine or a cosine curve making this oscillate, right? But if I think of the midline of that curve, it's causing another type of function, this other shape of function. So we have this shape and we have this shape added together to create this new shape. So I think about this, I'm like, oh, that looks like exponential growth. So we're going to call that exponential. And there's a couple different names for this. So I think the answer key says sine or cosine, but there's some more formal names. You can either call it trigonometric or sinusoidal. That's what we practice. Trigonometric or sinusoidal. And there's also sine and cosine, I guess, if you want to just say that. Okay, over here, same thing. We've got this oscillating, so we know it's sine, cosine. So again, trigonometric. It's a trig function or a sinusoidal function. And this shape is a parabola, right? So our midline here kind of is a parabola. So it's parabolic, sorry, so that's quadratic. All right, wonderful. Hopefully you already figured that out. All right, James wants to model the following data. So we have some data. Which type of function would best model this data? And give a reason for your answer. So I myself am very visual. So if I have this data, I'd like to draw a picture of it. So I'm going to draw an axis here. We have our x-axis, our y-axis. And when I'm at 0, I'm at 0. Okay. When I'm at 1, so it looks like my x's go 0, 1, 2, 3, 4, 5, 6, 7, 8. And we go 0, 40, 80, 40, 0. Okay, so I'm going to go up here. So this is, say, 0, this is 40, this is 80. Sorry, and that's my y. All right, so 0, and then at 1 I'm at 40, and then I'm at 80, then I'm at 40 again, then back to 0, then back to 40, then back to 80, back to 40, back to 0. Okay, so if I go like this and connect those, I can see what type of function that is. And again, it's trigonometric. Give a reason for your answer. Well, it has a cyclical nature. It cycles, meaning it has a periodic behavior. Remember, so one period would be from peak to peak. So that would be one period, or from middle to middle here, right? That would be one full cycle, one full period. All right. And then Robert states that this equation right here is a good model for this data. Is Robert correct? If so, explain. If not, modify his model to make it correct. All right, well, all we need to do is plug in a value or two and make sure that that works. So I have an x, I have a y. Here I have x and y data. So I think the easiest of all of these numbers to use, 0, 0 is probably the easiest value. So we're going to plug in a 0. I'm going to put a question mark because I want to know, is this equal 40 minus 40 sine of 90 degrees times 0? Whoops, not x, 0 times 0. Okay, so again, I plugged in x is 0 and I plugged in y is 0. And that should be a point that this model gives me. So let's check and see if that's equal. Okay, so 0 times 90 is 0. All right, what's sine of 0? If I think about sine, it goes like this. At 0, sine is 0. So here, this whole sine of 0 degrees is 0. So now we have 40 times 0. Well, that's all 0. 40 minus 0 is still 40. So here we have 0 equals 40. Is that a true statement? Oh goodness, no it's not. That is not true. So this is not a good model for that. So here it looks like the sign is underlined, and I feel like that might be a hint. Like maybe sine is not the right trig function to use. So let's try another. Why don't we try cosine and see what happens there? So when I look at the data that I plotted, I notice I didn't start at the midline. And that's what happens when I use sine, is I should be starting at the midline. And here, cosine, normally the ones we did, cosine started up at the top. But this may have been reflected, so it may be a cosine. All right, so let's try cosine. 40 cosine of 90, and I'm going to plug in again. I'm going to plug in 0 and equals 0. Great. So 90 degrees times 0 would be 0. What's cosine of 0? Let's think about cosine real quickly. Cosine starts up high, goes down, and back up. So at 0 degrees, cosine is 1. So this right here is 1 times 40 minus, all right. So here we have 40 minus 40 times 1, so just 40 minus 40 is 0, equals 0. Woohoo! So we were asking, is that true? And it is. So it looks like if we change that sign to be cosine, then the model fits that data. Now, I only tried one. Might want to try another one. Plug in 2 and double check and make sure I get 40 out, or 3 and double check and make sure I get 80 out. I guess I didn't consider this, doing this by hand, but technically you could plug this in your calculator and make sure that you are in degree mode and test some values with a trace function. So that's another option. All right. Cool. I think this is the last problem in this section. It's the box problem. All right. Okay. So Escher, ooh, like MC Escher. Cool. Escher wishes to make a rectangular box with a square base and an open top with 100 square feet of cardboard. He wants to have a box with a maximum volume. A drawing of the box is below. Escher lets x represent the length in inches of the sides of the square base. All right. As a part of the modeling process, Escher does a whole bunch of algebra and writes a formula for the volume of the box V as a function of x. And this is the formula that he found. All right, what is the domain of the function? Justify your answer. If I think about domain, for me, visually makes more sense. So I would maybe come down here and look at this graphically. But let's say we didn't have a graph. So one way of looking at domain is saying, okay, from this x to that x. That makes sense. The graph is here to here. But why only there? If we look up here, our volume has to be positive. It makes sense for our volume to be positive. So x, that's fine. We just don't want it to be negative, okay? If I put a negative number in there, it's going to end up being negative. But if I go 10 minus x, so if I take the second term, 10 minus x, what number would make that a negative number? So 10 minus 5, that's positive. 10 minus 7, that's still positive. That'd be 3. 10 minus 9, that's 1. 10 minus 10, that's 0. Okay, but 10 minus 11, if I put 10 minus 11, I'd end up with a negative 1, and then I'd end up with a negative volume, which doesn't really make any sense. So in the context of this problem, we only want positive values for our volume, so we're going to limit it to 10. This says, this really doesn't have much of a limit. This says we need to limit it to 10. So 10 should be our max. Then we look at the next one, 10 plus x. All right, if I plug a number in here, is that going to make this negative? If I plugged a negative number in here, or if I plugged a negative number in here, then that would make it negative. So I don't want any negative numbers. So I want x values greater than 0, and I want them to be less than 10. So a good interval would be between 0 and 10. If it equaled 0, that wouldn't really make sense because then you wouldn't have a box. So I would say it's not equal to 0 and not equal to 10, but anywhere in between there. All right. What is the domain of the function, and justify your answer? So I would say anything greater than 10. Whoops, I forgot an n in there. Anything greater than 10 would make the volume negative. All right, so notice what I did. I answered the question, I thought I was done, but then I went back and I reread the question just to make sure I answered the whole thing, and I noticed that I didn't justify my answer, so then I went back and I did that. It's really important that on the final exam, you're using these strategies, making sure that you answered the whole question. It's really sad to see a student who really understands it, but just didn't answer both parts of the question. So be really careful to answer both parts so you get full credit. All right, Escher makes a graphical model shown below. Approximately what size square would Escher use for the base, and what will be the approximate volume of the box? Okay, well he wants to maximize the volume of the box. So the highest peak point on this graph looks about right there. So I'm going to go down here, and this is really hard to see on this board. But I can see it on my paper that it's 5. It's closer to 6 than it is to 5. So I'm going to say like 5.6, 5.7, maybe 5.8. It's a little hard to see. So we're going to say about 5.8. So 5.8. Now remember, this was our x-axis, and on that picture of the box it showed x and x. So 5.8 inches by, oh, sometimes you use an x for that, by 5.8 inches. That would be the dimensions of my box. Approximately what size square would Escher use for the base, and what will be the approximate volume of the box? Oh, see, there it is again, a second part to the question. So here's the dimensions of my box and the approximate volume. Let's go back and check. Okay, so the highest amount is here, which is about right there, and it looks like between 90 and 100, closer to 100 than 90. So we're going to say maybe 96 or 97. So about 96. And we're talking in inches, and volume, remember, is length times width times height. I was going to say base times height, but length times width times height. So we have 3 dimensions there, so it's going to be inches cubed. All right. And the last step says, would a table be a good model for this situation? Explain why or why not. Well, a table, if it included every single value, would be the really, really huge table. So a table doesn't really make sense in this situation because you kind of have to limit the number of entries on a table. So I would say a table is probably not the best model. Why? Why or why not? All the values. I think it would be very lucky for us to actually get that exact value into the table. So a table has a limited number of entries. All right, so I mean, this is an opinion question, and you may have a little bit different opinion or a better way to describe it. But thank you for watching Unit 4 video. Good. I was about to say good luck, but you guys don't need luck because you're preparing very well. All right, test well. Read directions. Read them again at the very end. All right, happy testing.